and thanks for inviting me to talk here. It's really great to be here and see the work that's been done since the second Turing methodology and theory week. So my name is Ben. I'm a PhD student in Cambridge, supervised by Mark Trollomy. And this work's been supported by the Alan Turing Institute through the Turing Methodology Week, in particular the one in September, the Accelerating Generative Models and Non-Convex Optimization Week. So this is about a Python package, JAX, which you can go and use because it's online already. And so I'm going to go through an example to demonstrate how to use it. Hopefully it's interesting to you, and it might be related to some of the problems that you're working on. And if not, it should be easily extendable, especially if you're using unadjusted Langemann methods of some kind, and especially if you're using score matching methods. So denoising diffusion models are a high dimensional sampling framework, and DiffusionJAX is a Python package. It's open source, and it's a research tool to produce reproducible and replicable numerical experiments. You can sample from generative models using any dimensional data. It's not got many lines of code, so it's easy to extend to your problem, hopefully. And yeah, that's about it for that slide. So, so much of this presentation is based off the work by Yaakov Piszczegás, who's in the audience today. And it uses one of the examples from his work here on score-based generative models to take manifolds, and also see the score-based generative models introduction he's got on his blog. So if I get the time today, I'll go over some of the extended capabilities of the package, including using inner loops on your numerical solvers, whether that's for empirically better sampling, bias correction, adjustment steps, and then going over inverse problems such as inpainting. So what are denoising diffusion models? Well, there's two SDEs, the forward diffusion or noising SDE, which takes your data, and XT is chosen such that if you condition on one of your data points, sampling from XT is possible within one step of a transition kernel, and that transition kernel exists in closed form. So this could be, for example, an Ornstein-Uhlenbeck process. And then the generative model is the reverse SDE, which you can see. This is a animation from Yang Song's blog. Yang Song and co-authors wrote the paper Score-Based Generative Modeling for Stochastic Differential Equations. And so this is going from noise to data. And in particular, if the terminal distribution, the initial distribution of the reverse SDE is equal to the terminal distribution of the forward SDE, then the marginals correspond to each other in reverse time. But there's a problem with this in that we can't access the marginals of the forward SDE since we don't know the data distribution. If we did, and we could sample from it, we wouldn't need a generative model. So that means we can't sample from the reverse SDE because we don't have the initial condition and we don't have access to the drift. So denoising diffusion is an approximate answer to these problems. And the first approximation corresponding to the first problem is that the Ornstein-Uhlenbeck converges to the normal distribution independently of the data distribution. And therefore we can start the reverse SDE in the normal distribution. And secondly, we can train a neural network approximation of the drift using score matching. So this is the example from Yaakov's paper. Typically, we have samples. That's what we assume to have in this framework, samples from the data distribution. Here is a particular data distribution. It's a circle. So samples taken from the circumference of the circle. And as I said before, the forward SDE is chosen such that the conditional distribution has an exact transition kernel. And so in order to converge to the standard normal distribution in finite time, because we need to be able to use finite time in practice, they tend to rescale the time axis from sampling, converging towards the standard normal at infinite time to a finite time. And that leads to the introduction of this temperature parameter, and beta controls the rate at which you cool down your initial distribution towards the terminal distribution, which is the data distribution that you want to sample from. And so that tends to be quite important in the implementation in practice, So this is the first line of DiffusionJAX you see at the bottom, and that's an implementation of the Ornstein-Uhlenbeck SDE with some of these time rescaling temperature parameters added. So for this particular circular example, we've seen that the time t transition kernel is given as a Gaussian distribution. And if we assume that we have J samples from the target distribution, the empirical measure is the weighted sum of Dirac deltas. These are point masses that if we start the distribution of the forward SDE and diffuse, then we get the marginals PT hat of the empirical distribution as a mixture of Gaussians. And so a good question at this point is, okay, if we can write down the marginal distribution given the data of the empirical distribution, which is an approximation to the true data distribution, if it exists, why can't we just calculate the score of this, the gradient of the log marginal density, and plug that into our reverse SDE? Well, we can, and you should try it. So here is the gradient of the log hat density in JAX. But the problem is with this is that it's computationally intractable in large dimensions because you've got this summation over the whole data set right here. And so here is a plot anyway of that empirical score, and it's an animation, and you can see over time. So this is in forward time going from 1 to a small epsilon, and this would be the reverse time going from 0, the standard normal distribution, to some progressively more ill-conditioned distribution. And it's that diffusion process that will allow you to sample from multimodal, so nonlinear scores in the states or ill-conditioned distributions. So that implementation in DiffusionJAX is getting a sampler from a numerical scheme such as Euler-Maruyama, and DiffusionJAX isn't limited to that, obviously. And I think you can quite easily extend it to any like SDE numerical solver from other packages, even such as diffrax or SciPy. And then it implements, the implementation has a utility function in which you can get a sampler from that numerical solver, and then sampling from the reverse SDE, and plotting those samples over time using the empirical drift. You recover the exact marginals of the data distribution as t tends to 0. So actually, no, we're approximating this score, the nabla log PT, because it's intractable computationally to compute exactly. So is that computation going to be accurate? What's the error involved? Is it bounded? Is it unbounded? What kind of things happen? Well, these are the types of numerical experiments you can play with DiffusionJAX. So what if we add a constant error to the empirical drift? Well, the support of the distribution doesn't change, but the density on the support does change. Okay, so now if we use, instead of exact drifts, we're using score matching. And the objective comes from a Cal divergence between two laws of a stochastic process, one with the approximate drift S parameterized by the parameters of a neural network theta, and one with the exact drift. We can't evaluate that because we don't have access to the data distribution PT. So you can approximate that. And instead we use the following replacement loss with the empirical distribution substituted in. And then the step going from the left-hand side to the right-hand side on the second equation is score matching. And that is a result of vector calculus and integration by parts to show that that's equivalent. So now the crux of it is in the implementation is that you can evaluate this in constant time. And so memory cost of the size of the data set is now the limiting factor. So in DiffusionJAX, you can pick any Flax neural network model. Flax is a neural network library in JAX, and it's designed to be quite flexible. So if you wanted to do things such as parameterize your score to be linear in the state, to model convex distributions, or like a Gaussian distribution and nonlinear in this time parameter, then you can do that. I've tried that myself. So that's quite flexible. You can drop in any model, initialize the parameters, and optimize is given by JAX, a utility function again for the loss function, and train with score matching. Then we can plug in the train score, which I've plotted here again as an animation as forward time t1 goes to 0. And you can see it's not the same as the empirical score, which was exact. So there is some approximation error. So again, Euler-Maruyama solver for plugging this drift into reverse SDE, but any solver could be used. And in particular, in some of the literature giving best kind of sampling performance in terms of like how do these samples look visually, there is some work about using an inner loop, which has a Neo-Langevin step to freeze the dynamics in time and to sample from those frozen dynamics. But yeah, you could also have a bias correction step as an inner loop as well. So this is running the reverse SDE with the train drift, where there is implicit regularization in the learning of this score function through early stopping of a neural network. And it looks like it's recovered the support of the data distribution, but not only the support of the empirical samples, but also is interpolating in between. And so it would be quite interesting to know why stopping the training of stochastic gradient descent over the network weights earlier would produce a score that, as time tends to 0, looks like it's pointing towards something that interpolates between the data in a smooth way. And if you keep training, why this score would tend to get better at a more slower rate to point towards the exact data. So that's what happens if you don't have early stopping. So to install this package, it's made quite easy. It's on pip, and the instructions are available on the GitHub. And as with any collaborative open source project, they tend to be better the more collaborators there are working on them. So if you're interested in collaborating or applying it to your problem, send me an email or a message. So my email is bb515@cam.ac.uk. Yeah, and I'm happy to answer pull requests and issues on the GitHub itself as well.